the basic setup for our shack cube that we're using in this lab. We have light coming in from our laser, going through an objective and coming into our shack cube. Some of the light from the shack cube is coming up and then reflecting right down to our image location, and the other light is getting transmitted up to the test optic and then being reflected down into the image location. And this creates two very different path lengths. The first pass that just comes through and then goes right down to the image location, and the next pass comes through, goes all the way up to the test optic, and then comes all the way down. So these two very different paths that we have here are the two optical paths that are interfering to form our fringes. So for this setup, we have the confocal focus, which is where light coming in is perpendicular to the surface, so it's coming out in exactly the same direction. And when we have our test mirror positioned at this location, when we have spherical wavefronts coming out of our test optic and propagating through our system.
These are a few comparisons between the shock cube and the shear plate. With the cube, we only need one high-quality optic, which is provided by the curved surface previously discussed, whereas the shear plate is better suited to test optics. We experience a large OPD with the shock cube. It is more sensitive to disturbances, which we will later show, and it also shows the wavefans as opposed to the rate error on the screen. This is an example of defocus, what it looks like on the shock cube, and what it looks like from the shear plate. As you can see, this is the equation for defocus. We expect a parabolic shape. This is the top view. And then if you take the derivative to obtain the rate error, we obtain the equation for a line, and these are the lines that we get for defocus.
This is our experimental setup. We've got a laser. It comes into the spatial filter. We've got a microscope objective that makes the beam divergent. It comes into this shack cube, which is a beam splitter with a lens pasted on the front. It gets the divergent beam and reflects it this way. Then the beam is split up into two beams. One part is reflected back this way, and the other beam refracts through this lens and hits this test mirror such that it's in the center of curvature of the test mirror, so that it retroreflects right back on itself. And now we've got two beams that overlap. If this test mirror has a perfect spherical shape, the two beams that overlap won't interfere, but if there are any aberrations present, we'll see interference. Okay, here we're at best focus. What we did was we added defocus and tilt and observed the fringe patterns to analyze what kind of aberrations were present. Right here I'm going to add a little defocus, and you can see that even though I'm just adding defocus, we get tilt because the center is offset in the image screen. Our setup was very sensitive. If we touch any part, the fringe pattern would disappear, and it was very hard to align everything. This next part of the experiment, it was the exact same thing. We just substituted this mirror. The last mirror had a long focal length, and this one has a short radius of curvature. You can tell by where it focuses. It focuses somewhere towards the end of the shack cube, and we did the same analysis by adding defocus and tilt and analyzing the interferograms.
These are the results that we obtained in the first portion of the lab. This is the fringe pattern that we obtained when we applied defocus. This is the fringe pattern that we obtained when we apply tilt, just tilt by itself, and this is the combination of the two, and this is exactly what we expect to see. For the second portion, this is the defocus fringe pattern. We weren't able to resolve any of the fringes when we applied tilt using the camera, so we couldn't get a good picture. However, this is defocus and tilt.